Adversarial filters of dataset biases. Let's talk about the motivation of this work. The main concern that this work is trying to address is that when it comes to training large neural models, even though they often perform really well, their performance degrades considerably when it comes to out-of-distribution samples, meaning that we don't really want a model to learn a dataset, we want it to learn a task. This work contains theoretical and experimental analysis of AF-Light, which was a model proposed previously to adversarially filter such database biases. The results of this paper actually confirms that AF-Light is a great algorithmic framework for this purpose. The main problem in training that this work is trying to address is overfitting to spurious biases, defined as unintended correlations between inputs and outputs. Some of the problems that these spurious biases cause can be mentioned as biasing the models and also significantly inflating the model performance. To deal with this work is focusing on investigating AF-Light, which is an approach to algorithmic bias reduction. And its goal is to systematically discover and filter any dataset artifact in crowdsourced common sense problems. Now, what this paper adds to it is the first theoretical understanding of it, and also more comprehensive empirical investigations into AF-Light. To summarize their contributions, they first discuss AF-Light in a theoretical framework for optimal bias reduction, and discuss that AF-Light provides a practical approximation on AF-opt, which is the ideal but computationally intractable bias reduction method. Second, they perform more comprehensive experimental studies using this AF-Light, containing both synthetic and real datasets. And as you can see, their studies span over different tasks from various modalities. The third thing they do is diving deeper into understanding the generalizability that results from using AF-Light and the datasets filtered by it, which exhibits substantial better performances. Lastly, they show that when it comes to AI benchmarks, using AF-Light filtering actually leads to decreases in the performance on the in-domain tasks, which could be an indicator that the performance on these benchmarks might be inflated by such biases. Therefore, they propose that AF-Light filtered datasets can serve as upgraded benchmarks. When you have a large dataset with a data-rich head in the distribution of its data, there is the risk of prioritizing performance on those parts, which is what AF-Light tries to prevent, and it tries to preserve the complexity of the tail of such distributions. Consider a dataset D, and consider phi being a custom feature representation over it. The AF-Light algorithm wants to take this dataset and these features and return a subset S of this dataset, such that S is a subset of D and the cardinality of S is larger than or equal to N. That is, maximally resilient to the features discovered by phi. Consider that you have a held-out validation set. You are looking for a S set such that no matter how you break it down into test and train splits, learning how these features are in the training instances of the train set of S should not be adding something of value to the generalization performance on a held-out validation set. Say that M be a family of classification models, such as SVM, etc. And these models can be trained on subsets S of D, which was our dataset, using features phi x. They define R of phi and S in M, named representation bias of phi, in S and with respect to the functions family M. This is the best out-of-sample accuracy when using features phi x. Now let's say you're looking to reduce the dataset more than n instances. Thus the algorithm is going to look for a S of D with a cardinality of at least n, such that it satisfies this equation. Meaning that it minimizes the best out-of-sample classification accuracy achievable by phi on the subset using the classification models in the model family M. Now this would be the optimal bias reduction, known as AFOPT. Now, they offer a slightly different definition of R. Their formulation of R of phi in S and M, or representation bias of phi in S with respect to M, is defined this way. Consider Q be a probability distribution over all of the subsets of S. These subsets can be written as T like this, with xt and yt, meaning that the examples in the subset and the labels in the subset. Such subsets will be sampled from this distribution Q, and then classifier MT from this family of classifiers will be selected and trained on the rest of S, and then it will be evaluated on the subset T. With all this in mind, they define the representation bias of phi in S with respect to M as the average, the expected value of the subsamples T, their evaluation result, like this. So by randomly sampling this subset and then computing this overall average, they define the value of the representation bias of phi in S with respect to M. This still has the problem of being combinatorially difficult because you have to look at a large number of T's. In order for these modelings to be computationally tractable, they want to shift the focus on examples instead and use the aggregate contributions of each instance I to the overall representation bias across all of the T's, instead of going over and looking over all of the combinatorial options for S and T. Having a subset S of D and T being a subset of S, they define predictability score PI for instance I that is a member of T that has to do with how reliably label yi can be predicted using features phi xi, given that a model MT that is trained on ST is going to do this operation, noting that this does not contain I. The desirable examples are those with a low predictability score. Consider QT the probability of subset T being selected from S. They define QI this way. It basically is the marginal over these subsets such that those that contain I are selected. So this is the marginal probability of choosing a subset T that contains I. Now considering QI, you can define this ratio, which basically limits it to a conditional definition of selecting a subset T conditioned on the fact that it contains I. Now we can write as follows. The definition of representation bias of phi in S with respect to model family M was this average, which in turn can be written as for all subsets So here you have the probability of subset T of S being selected, and then it has the cardinality of T times items. And then for each one of these items, you have this value of prediction, which has to do with the classification accuracy. So for each T, you compute basically this average. Now, instead of combinatorially going over T's, now let's move the summations a little bit and write it as this. Now they want to write it as for each item in S, and this time selecting T's such that these T's contain I. And now look at these aggregate contributions. Now they can multiply and divide by Qi and write it as for each I in S, they will have Qi, which was marginal probability of choosing a subset T that contains I, and averaging over subsets of S that contain I of this value. Which they define as predictability score of I. And for simplicity, they consider Q to be uniform distribution over all of the subsets of a fixed size. With this definition, the predictability score of I will be defined as the marginal probability of the subset T containing I being selected times this average. Meaning the average of classification accuracy of predicting labeled yi over these subsets that contain I. Now they consider Q to be uniform distribution again. So in particular, the marginal probability would be as, so all the cases are the combinatorial selection of T from S. Now consider I already exists, so T minus 1 minus S minus 1. So this will be this ratio. So with this assumption, which was the uniform assumption over the uniformity assumption for the distribution Q over fixed size subset C of S, they will prepare a factored reformulation of the representation bias where they define this predictability score of I like this. And then they use this to define this new version. Okay, now let's discuss what has actually happened. With the given definition, which is this, now this part and this computation is now tractable because we no longer have to go over combinatorial options for T. Now the computation for equation 1 is still problematic because we still have combinatorially large options for S, and searching over possible subsets S of these is still problematic. However, this refactoring enables computationally efficient heuristic approximations. And the way it works is that it starts with S equals D and iteratively remove the most predictable instances from S until obtaining the final desired S. A of light in particular used a greedy slicing approach, meaning that in each iteration it considers the k highest probability scores and removes all of them and does this k times, basically d minus n divided by k times, so that it ends up with S with a cardinality larger than or equal to n. And this can be a scalable and practical approximation of AF opt. Here is the algorithm for the AF light. Let's go over the different inputs. So one input is the dataset D, X, and Y. There's the pre-computed representation phi x. There's a family of models M. There's the target dataset size N. This is the size that the cardinality has to be larger than it. And then the number of random partitions M. There's the training size T inside these S, so T has to be less than N. There's a slice size K, which has to be less than or equal to N, and there's the earliest slapping threshold tau. And the output is going to be the reduced dataset S. So the algorithm starts with S equals D. As long as the size of S is larger than N, it continues. For each instance in S, it initializes a multiset of out-of-sample predictions EI. So it does this block M times. In each time, it partitions S into TJ, S, and TJ. So basically, you have this subset TJ and its complement in S. They pick a classifier from this family of functions and they train it on this. Basically, they train it on the complement of TJ in S, which is typically a linear classifier. Then for all of these samples in TJ, they add these predictions to the EI. And after doing this block M times, they go here. Now for each item in S, they consider the predictability score of it by how many times this prediction that was done was accurate. Now they select up to k instances with the highest predictability score, and they remove them from S and they continue. They also have this early stopping threshold, meaning that if all of these items fall below this threshold, this condition also gets satisfied and the algorithm breaks. This figure is an overview of some of their synthetic experiments. They synthesized datasets with different levels of separation, this part being the highest. In this part, in the highest one, they basically flipped some of the labels at random so that a radial basis function kernel can also not achieve the perfect performance on it. This would be the dataset that is input to the AF Lite, and this is the result, which is the filtered, more challenging dataset. To simulate these unwanted correlations, they picked two different Gaussian distributions and basically added these artificially constructed features to 75% of the data in each one of the classes. While for the rest, meaning the rest of the 25% for each class, they used random noise. The results depict this inflated performance, meaning that these unwanted features are actually utilized by especially by the linear classifier on the actual dataset, while the AF Lite version of the dataset makes it more challenging, leading to the more realistic performance. And by realistic, meaning that for the out-of-sample distributions for which those unwanted features are not present and not important, these results would be more accurate than the inflated performance reported on top. For their natural language processing experiments, they focused on the natural language inference task as their main one, for which they used the Stanford NLI dataset. In the NLI dataset, the task is to predict one of these three labels: entails, contradicts, and neutral on a sentence pair. For the features, they used the features from Roberta. Now, they considered a zero-shot SNLI accuracy on 3 out-of-distribution evaluation tasks. This means that on these 3 datasets, the task is the same, but the spurious biases possibly learned in the SNLI dataset are less likely to be present. And you can see the superior performance. Now, this 182K, it means that, so the original dataset had much larger cardinality, but the one that has been the result of applying the AF Lite on the 5 Roberta features of this dataset has a size of 182K. The 182K here is a random subset with the same size, just to better explain the impact of using this algorithm AF Lite and obtaining the filter dataset. When it comes to in-distribution, however, they show a reduction in performance, seeming to confirm the hypotheses that the models have been training and learning the dataset more than they were focused on the task. For their computer vision experiments, they focused on ImageNet dataset with the EfficientNet B7 model to help extracting the features. The results, for example, on the ImageNet adversarial training dataset is that the most efficient model, the EfficientNet B7, improves by 2% if trained on the AF Lite filter data. The same performance drop is also present in the image task. All in all, they explored the theoretical and experimental aspects of AF Lite and provided a theoretical framework for supporting it. And they used synthetic and real datasets to prove that it actually works.